Good afternoon, everyone. My name is Tim Chung. I'm a former DARPA program manager in the Tactical Technology Office. It's my privilege to be here today. I'm really excited to be here. I was previously the program managers for the Offensive Swarm-Enabled Tactics program and the DARPA Subterranean Challenge, and I think you saw a little bit of that yesterday. Currently, I'm the general manager for robotics and autonomy at Microsoft. And so on behalf of this panel, the Breakthrough in Field Robotics, we're really excited and really grateful to DARPA and to Colorado State University for this opportunity to have this conversation that is really near and dear to my heart associated with field robotics. And particularly, I want to thank everyone here to engage in that conversation. This panel is really about exploring and having that conversation about the possibilities that may constitute the next breakthrough or breakthroughs in an area we like to call field robotics. One of the goals of this panel is to kind of shed light on some of the future challenges and explore ways that DARPA can accelerate their development beyond some of the things that we've already seen to date. And so the panel members will take a few minutes to provide a little background on their own work, but really want to engage with this audience through your questions and through questions that I'll be asking the panelists. We'll have this chance to have some good comments. So let me go ahead without any further ado and introduce our panelists for this afternoon session. We have 4 panel members, and the first up is Dr. Ali Aga. He is a robotics technologist and group leader at NASA's JPL, Jet Propulsion Labs, Autonomous and Robotic Systems Division, and also at the Caltech Center for Autonomous Systems and Technologies. And his focus is in autonomy and AI with a dual focus on planetary exploration and terrestrial applications, dovetailing the role of DoD in space. Dr. Aga led Team CoStar and a number of solution areas for the DARPA Sub-T Challenge, where the CoStar team placed first and second in the tunnel and urban phases of the Sub-T Challenge. We're glad to have him here with us today. He's also leading JPL's team for DARPA Racer, which we just heard about earlier as well. Okay. Next up, we have Dr. Sebastian Scher. Dr. Scher is a systems scientist at the Robotics Institute at Carnegie Mellon University. His research focuses primarily on unmanned rotorcraft to operate at low altitude in extremely cluttered environments. And his background stems from his significant time at CMU. He's numerous recipients of awards and recognitions, specifically focusing on field robotics, including his self-landing helicopter work that received the Popular Science Best of What's New award, which is great. Next up, we have Dr. Weni Tabib. She also got her degrees in robotics at Carnegie Mellon University. She's a systems scientist with the Robotics Institute at Carnegie Mellon University, and her primary area of interest is in perception, planning, and learning algorithms for enabling safe autonomy, and in particular, operating safely in 3-dimensional complex environments. And so the main idea here is understanding the 3-dimensionality and the complexity that brings to the types of robotic solutions we really need to bring to bear. She's also a member of a number of grottos as a caver by hobbyist as well. And our 4th panelist is Kyle Usbeck. Kyle runs the autonomy group at Systems and Technology Research as a principal scientist, and he leads the R&D efforts focused on collaborative autonomy, which we'll have a chance to hear about here today. The idea behind collaborative autonomy is that we can enable autonomous robots to cooperatively accomplish their shared objectives. And his experience working with DARPA includes the Offset program, Squad X, C3D, PCAS, and META. And even I don't know all the acronyms for what those represent. But his background really stems from being out in the field and contributing to advancing field robotics. And so before we begin with our panelists, I wanted to take just a quick moment to ask each and every one of you in the audience, both here and in virtual land, to find a way to ask your neighbor the following question, which is whether you've either read about it, seen it in a movie or TV show, or you've just dreamed up a fantastical idea. I'm curious to hear your thoughts on what recent advances in robotics that you all are excited about. So if you'll spend the next couple minutes talking to, let's say, your neighbor on the right, ask him what excites him about robotics. This is just to prime the pump. We'll flip it around, turn it to to your left and do the same exercise, and we'll go from there. Please take your time.
We just start.
Okay. And now if I may, I love that robotics is this exciting a conversation topic. It's really great. So I'm going to have you switch partners now, right? Now go to your left. Or if you're having such a vibrant conversation, keep on going. But we got another 2.5 minutes to keep talking about exciting robots. I think the buzz in the room highlights that 5 minutes is clearly not enough to have a conversation about robots. And so to carry on that energy and bring it to the stage here with our fine panelists, eager to get that conversation started, but really appreciate the chance to hear, at least through from a distance, some of the conversations about robots. Before we dive in, I think I wanted to kind of set the stage and do some level setting about when we say field robotics, what does that really mean, and how does it distinguish itself from perhaps other robotics disciplines? And so when we're talking about field robotics, the panelists and I have highlighted that when we're talking about robots, field robots, we're talking about robots that operate in cluttered and unstructured and dynamic environments. And it's really that unstructured nature and the dynamic, uncertain environment that really gets to the heart of field robots. And so field robotics, these are systems that operate outside the built environment. The ambient conditions cannot be controlled. Scale is typically much larger than what you might find indoors. And these applications are everywhere, and we're seeing that both happen in our everyday lives, but certainly at the forefront of Department of Defense application areas. These applications include everything from construction, forestry, agriculture, mining, subsea, scientific exploration, search and rescue, and then, of course, military and what we just heard, space missions as well. And so finding ways that we can understand the nature of field robotics is at the core of this panel discussion. And so this research in field robotics, it spans and really is about systems. It's bringing together sensing, mechanical design, computing architectures, communication and RF, planning, learning, and control. And so without any further ado, I'm going to bring it over to our panelists here, and I'm going to join them here on stage. Check. All right. And so the first question for the audience, or for our panel, is what are the significant unsolved field robotics problems that would significantly benefit the field or practitioners? So this is really out of the gate a really tough question. Let me start with Winnie.
So I think an area of robotics that hasn't been really well addressed in the past is in active perception. Active perception is a way for the robot to take in sensor data, figure out which streams are useful, create internal representations of the world, and then figure out how to take actions that increase the robot's information or increase the robot's knowledge about the world around it so that it can make intelligent decisions. And so I think really we need to expend more resources in that area in order to be able to get robotics to in a more diverse set of environments, like our homes, in construction, and yeah, so more resources need to be devoted there to generalize robotics.
So as we said earlier, it's not just about one area of technology. It really is a holistic perspective of robotics. Another area might be, let's say, uncertainty, and how we deal with that in the real world. Ali, any thoughts on that?
Yeah, sure. I think one thing differentiates field robotics from many of robotic deployments in environments that you have designed for robots is that in field, really, there are a lot of unexpected events. You rely on models that you have had developed computationally on the paper. You go on the field, the models are quite different. And methods that be able to deal with that uncertainty in a systematic way and enable, a reliable operation of robots is, I think, a big challenge in front of field robotics.
Yeah, in dealing with uncertainty, finding ways to have uncertainty awareness in our robotic systems and our autonomous capabilities seems to make sense. Basti, what do you think about the hard problems in field robotics?
Yeah, I mean, I think kind of building on top of this is essentially resilience for these systems. If you have a lot of uncertainty, like we talked about, right? Then you want these systems to continue to operate. And this morning we talked about resilience for supply chains. There's one part of it is redundancy, so you have more than one source, but it's also having robustness in the system, having things be tolerant to changes. And then I think the part that's kind of hardest and where we spend a lot of time is resourcefulness, right? So which kind of comes in the end down to the robot being creative in a sense, right? So it has to be able to figure out, okay, I can't do something, my designer thought of something, but I'm experiencing something completely new. Can I come up with an action that gets me out of trouble?
Yeah, interesting. I heard the analogy where having robots read or listen or play music according to a sheet of music like a symphony orchestra versus eventually getting robots that can be their own improvisers and play in a jazz ensemble, being able to riff off of what the feeling is, right, or what the circumstances are.
And it's something humans are very good at, but robots are not. And if you want to have resilient robots that can make progress in uncertainty, you need them to be able to explore and new actions.
Yeah. So speaking of jazz ensembles or whatnot, what do you think for field robotics and maybe cooperative or collaborative autonomous systems? Any thoughts there for field robotics?
Yeah, thanks for asking, Tim. I would say that too often we as the field robotics community are met with a challenge, and we go right to our default response, which is we need a better robot. We need to build and design a better robot, and better robots are always great, but there's another option, and that option is to enable those robots to work in teams collectively, and those can help improve. Working as a team can even help improve the individual capabilities of an aircraft or robot. If I could give you a quick example.
Please.
We had a robot a few years ago that had a very limited sensor range, and as a result, it couldn't fly very fast without overflying its sensors and ultimately running into things. And so what we could have done is built a better robot with a longer sensor range, but instead, what we did was we built a cooperative behavior, paired it with a robot with a longer sensor range, and had them both work together to achieve nearly their optimal flight speed.
Yeah, and I think that's going to be topic of conversation here of what is it about these scenarios or topics that you've mentioned that sets it apart from other robots, right? What about the robot that's going to eventually get our groceries for us or whatnot? Is that, how does uncertainty and resilience and things like that come into play? I think another question that typically comes up is, which of the two are more the limiting factor for breakthroughs in field robotics? Is it the robot body, namely hardware-based solutions, or is it the robot brain, which is more of the software side? So Ali, I'll start with you.
Sure. I think definitely improvement in both of those domains would benefit field robotics quite a bit. We need better hardware, better software, but the one, if you want to pick one that is more limiting, I would say definitely software. And so one test usually I have in my team when we are trying to benchmark an autonomy AI algorithm is we say, okay, if I give you a hardware, a robot, let's say Boston Dynamics, a spot robot, a wheeled robot, a drone, and a joystick, a controller to a human, what can you do with it, right? And if you're able to do more than what our autonomy and AI does, it just shows that locomotion, mechanical capability at least is there to a certain extent that we are not able to exploit that or use it with AI and autonomy. And if you look at our robotic system, physical embodied vehicles, that's almost 90% of the time is the case. We can do way better if we give the joystick to human, even if you don't see the robot, even if you just get the raw measurement and from a screen control the robot, human does much better, which means that AI-wise, autonomy-wise, we are behind, more behind than our hardware, and we can do much more with the current platforms that we do have. So in that sense, I would say limiting at the moment is software.
Sure. Well, Winnie, I know all of us here have both built and broken our fair share of robots. So what are your thoughts? Is it the robot brain or the robot body?
Oh, it's the brain for sure.
Okay.
At least in my experience, yeah. You're limited by how much data you can process. You need to process data as quickly as possible to get the best performance. So part of that is the hardware. But even if you have better hardware, typically it's larger, so you need to use small size, weight, and power constrained computers. So you're already relegated to fairly small computers, and you really just need to build more efficient algorithms in order to be able to get those robots operating at peak performance.
What about you, Basti?
Yeah, so I think, I mean, I definitely agree with the software part, but I think we are also limited on the hardware side, right? I mean, there's limitations in, let's say, cameras, IMUs, computing, where these things could be step functions to kind of a next level thing. And yeah, we definitely don't exploit what we can. The software is behind, but hardware can also help.
So kind of riffing off of what you just said, is the speed of development in the hardware side either keeping up with or exceeding the speed of development on the software side? Is there a pacing function here that dictates that?
I mean, the way I kind of see it we are kind of riding on the tails of the cell phones and a lot of self-driving and these investments, right? Like camera sensors, computers is kind of what we are benefiting from. Yeah.
Yeah, I think the autonomous vehicles conversation earlier, where Velodyne started in the DARPA Grand Challenges well over a decade ago, and now we're flying around or driving around with a bunch of these LiDAR units on board. Do you have a particular take, Kyle, on hardware versus software?
Yeah, all the other panelists are certainly make great points. I see robotics not as only about robots, and so we're at an exciting time in the field robotics community where we're starting to see platforms emerge that have the ability to sense important phenomena and navigate some complex environments. And what we really have is a responsibility to advance autonomy to the state that we're able to really allow those robots to make difficult decisions and then also to work together in teams to accomplish shared objectives.
Yeah. So algorithmically speaking, what do you see as the main challenges that will enable that resilient, perhaps multi-robot system in the real world settings? Basti, what are some of those headaches?
Yeah, I mean, I think the way I sometimes think about it is you can think about, when you design an algorithm, you think about an operating envelope. Like if you have a plane, you have some operating envelope. And so how does your algorithm behave outside of your envelope, right? And if you have a very simple algorithm like a control algorithm, it will behave reasonably nice outside of your envelope. If you have some of the algorithms we're looking at right now, they will just give you some random answer, right? And so this kind of how to behave at the edge of the envelope, I think, or outside of the envelope, is I think where a lot of this resilience comes in, because you couldn't think about it as a designer when you thought about it.
Yeah, so baking that in at the algorithm levels,
right,
as part of the design.
It's a very abstract answer, but it comes into the various pieces.
Yeah, well, and that kind of speaks to how early you need to co-design and think through the implications of those applications, but also the uncertainty associated with it. Ellie, same question. What are the main algorithmic challenges you see out there right now?
Yeah, sure. I think tying it back to the previous question on software, one of the reasons maybe we are a little bit behind on the software side is because there's some fundamental problems in algorithmic side of field robotics have not been solved yet. And I think we do have control theory, communication theory, very established fields. I think in a decade from now, we are going to have autonomy theory, that there will be textbooks and so on. And I think the part that is missing is, which today is being done as an art or engineering, but there's a limit to that. But we need to take a step back and do fundamental work on is the science of autonomy, which looks at co-design of different modules. In lab, in a laboratory setting, when we do deploy robots, we can abstract certain pieces, abstract perception, just work on planning, abstract certain things and focus on one part and show it's great. In field, you can't cheat. Everything comes together. Any imperfection in one domain affects the other one. And if your system is optimal but not resilient and a little bit, perturbs, with a little bit perturbation, changes its behavior significantly, then that's, I think, one of the most important causes of brittleness in today's autonomy. So there's that theory is needed to come and say, okay, if I have two systems, how they interact with each other and how I co-design them from the beginning rather than design them jointly and put them together.
Yeah. Wendy, what are your thoughts?
I think that in order to get robots to operate over longer durations, we really need to develop algorithms that enable the robot to sample views or obtain information when it is uncertain about its state. So as people, whenever we're not certain about something, what do? We try to acquire new information. So I think the key for robot algorithms is developing those technologies to enable robots to introspect and then sample views and locations to obtain more information.
Yeah, introspection for our robots, it's an interesting, I'm going to just go on a tangent here. Now, what does it mean for a robot to understand about itself? And maybe is there a human analogy there? Bastia, you have any thoughts on what introspection for robots might look like in the future?
Right. I mean, I think there's when you design these architectures, you have a certain thing in mind, and then each of these modules typically would have some kind of watchdog or variables you're looking at. And I mean, right now we hand design these things, right? Where it's like, okay, if this fails, then these downstream modules will not work. But I think in the longer term, as these systems grow, this has to be automated, and there has to be more reasoning done, because sometimes these kinds of failures or limits are not obvious, right? Like if it might be that a sensor failed, it might be that there's a bug in an algorithm or some bad network or something like this. And
do you find that is harder because we're in the wild? Is that the crux of field robotics then? I mean,
yeah, I'd love to take that if you don't mind.
Go for it.
Yeah, I think Basti hit on a great point, which is failure is omnipresent, especially in field robotics, and so what we need to do is really take those failures and account for them at every stage of the R&D process, and also learn from them, and not make those mistakes hopefully again in the future.
Yeah, I feel like that's a tall order, though.
Yeah, absolutely.
Understood.
Easier said than done.
Easier said than done, for sure. And so I think, field robotics, we could argue, we've been deploying robots for a while now, and there are many cases where we've seen robots being used quite successfully in some cases. Are there still problem areas that have not historically been addressed by field robots where we think that field robotics can have a market impact? And so I'll start with Winnie.
So when I go out in the world, I look at what people are doing and I ask myself, how could a robot do this? How can we get robots to do the jobs of, for example, traffic controllers or roofers? And I think one of the key areas that really hasn't been looked at deeply in robotics is this coupling between perception and planning, where the robot has the ability to adjust where it's observing the world and taking data and reducing its uncertainty about its environment model. So that field or active perception is I think one that hasn't really been well addressed in the past, but can lead to a large amount of robotics innovation and lead to robotics just being more generally found in the real world.
Yeah. What about you, Ali? Any other thoughts on that?
Yeah, I think one of the areas maybe we haven't historically looked at would be on semantic understanding. So as robots in the field being adopted, we are running and operating in more complex missions. I think the need to go beyond geometry is becoming more apparent. We have been traditionally heavily on relying on geometric reasoning of the environment in field robotics. Now with the new tools from ML, machine learning, and deep learning, now we are able to, we need to be folding more of semantic understanding of the environment into the autonomy, and maybe go beyond that and look at the relationship between semantics and different objects and understand the context of the environment. Maybe it's the same objects in the scene, but you understand, okay, now I'm in this room after a fight, or I'm in this room before a panel or a talk. And using that context to enable, maybe more long-term operation of these systems. You deploy them, even if context change, semantic change, they can adapt themselves over time. Something maybe we haven't looked historically enough at it.
Yeah, makes sense. One area I'll throw out there, just moderator's privilege here, is human-robot interaction and the interfaces of how we can work with and operate field robots specifically, as it distinguishes itself from other types of robotics. So any particular thoughts on how HRI, human-robot interaction, is significantly different or more difficult in the field kind of context? Kyle, I know you have some battle scars associated with field robots.
Yes, yeah, and human-robot interaction and human-machine teaming, very, very important aspects that we have to really work towards. There's so much there that I don't know if I can do a lot of justice in a short time.
Sure, I think one of the things we've seen in our various programs has been what happens when the robot no longer can reach back to the human. And that's either for mission commands or it's to relay information, right? And I think that's one of the main places where we had great information for our robots deep in the sub-T finals course, or we had robots that were collecting surveillance information, swarms of robots collecting information, but they couldn't all get that back because either the pipe was too narrow or too thin or too broken. What are some other pieces of that human-machine teaming element do you think could allow for breakthroughs in field robotics if we were able to solve some of those? Wendy, do you have any thoughts?
Yeah, I've been really interested in how a robot might be able to infer intent from a human. So like, imagine the robot is supporting, or a team of robots is supporting a person navigating or exploring a building after, like during a search and rescue scenario, or even on a battlefield. Without explicitly commanding the robot, maybe the human just looks at a doorway and then the robot goes in there and explores it for him, or explores parts of the environment that they're too tight for the human to access. But yeah, that's a very specific example, but it's one that I've been really interested in recently. How do we do that?
Sure, yeah, it'd be great to send a robot into a small cavern or something that a person can't get into, for sure. And so given our engagement with the broader community here, I'm going to ask this question. Are there investments that the government, industry, and academic partnership arena that we could make that could accelerate the growth of field robotics and or accelerate how much impact can be made? So can you give some thought, can you express some thoughts on how those partnerships, what would make for a really fruitful partnership there? Ali is representing JPL as an example.
I mean, field robotics is a really hard domain just because it's at the intersection of a lot of different domains. So in general, and it does require a lot of testing with hardware in the field, and it's resource-wise, it requires more resources than other branches of robotics. And I think in terms of investment, definitely would be great if there are programs or ways or types of incubators that looks at the ongoing cutting-edge field robotics efforts and try to bring the people together, have this sort of speed dating between performers and technologists with the customers, with people that needs to use it, so that this relationship gets more frequent, this communications, and the technologies that being developed in different cutting-edge projects actually find their ways into to make positive impact on society. I see that there's that gap that we build things, really cool technologies, but then robots are in the lab after programs end. And what I think the investment in that to bridge that gap would be really helpful for the community.
Yeah, for sure. As I've visited your lab, and you have a lot of robots in your lab, Basti, as an example from a university perspective, what kind of partnerships might make sense to help jumpstart?
So I think specifically from a field robotics perspective, I think infrastructure and kind of difficulty of making field robots is, I think, too high. Like, I mean, we can do it, and a lot of people can do it, but it takes a lot of time. It takes a lot of money to build these field robots, and I think there's a lot of infrastructure and tooling, or if it's like real to sim, sim to real, that's missing to really have this rapid speed of building new robots. Like for a lot of field robotics, it's also a co-design problem, right? It's not just, I'll buy this robot and put my algorithms on it. It's, I'll have to figure out, what are the sensors I need to solve this? How do I put them there? And then you really want good simulation associated with this. And I think related to this a little bit is, replicability of kind of the research we do. It's a little bit of a problem because a lot of the things, unless they're standardized platforms, as in some programs, it's one robot versus another robot, and there's so many differences, it's hard to know what's really going on.
Yeah, I think reproducibility is something that we'll all agree that field robotics just makes hard, because no experiment run is the same from one run to the next, and then it's hard to do A/B style comparisons, apples to oranges. Kyle, any other thoughts on this part?
Yeah. So I think there's, there are a lot of investments that are being made in the industrial and commercial sectors too that we need to take advantage of, and that's really key. Over the next couple of years, you're likely to see individual platform autonomy improving a lot, and that's going to enable some of the collaborative autonomy and the ability to accomplish shared objectives. That's really going to have some of the interesting and exciting new breakthroughs.
Sure. Yeah, Winnie, any additional thoughts on other things that would be accelerating for the field robotics community?
So I think, if you recall that having the open source middleware ROS really accelerated the trajectory of robotics, because anyone could start prototyping and developing at least robotic software. So I think the key to developing industry, government, and academic partnerships is increasing transparency, both for the hardware and software side, so that we can collaborate together on systems and increase the openness or the availability of these technologies, because that really drives innovation, is increasing the availability of these fundamental technologies.
Yeah, no, definitely. So I heard infrastructure, reproducibility, and then that transparency or availability of technologies to help reset that level to a higher bar for getting into field robotics. So thank you. I wanted to now turn it over to audience questions, and we already have some in the hopper here, and I'll go ahead and ask these tough questions to the panelists. Looking at the previous challenges and other programs that have involved robotics in the wild, the question is from the audience: what should be the next great DARPA-sponsored field robotics experiment, and what should be the most significant outcome of this event? So maybe that's the salient part. That's a tough question. As a former PM, I can tell you that's not easy. So Ali, I see you pensive over there. What is the next best DARPA-sponsored field experiment?
I mean, it's a hard question because there's so many.
Yeah.
Maybe would,
So if you had to pick, where would you love to go do a field test?
I think a push on having multi-robot systems running real-world missions would be something I think that can have a direct impact on on today's problems that we have both in industry and in DoD side. I would love to see another challenge or another program that would come with some, maybe ideally with predefined robotic platforms with some integrator teams, but come in and put in front of the performers or the research community a mission, and helps the teams focus on autonomy and enable this multi-robot mission. I would say that would be an interesting next field.
Sure. I half expected you to say you wanted to see it on the moon. But
Absolutely.
okay, just making sure that's still on the table
but,
for you.
But yeah, that's a little bit more on the dream side. So
All right.
I'll wait for the frequency of launches go up.
Sounds good. Wendy, what are your thoughts on the next greatest DARPA-sponsored field experiment?
I'm going to answer a little bit selfishly. I think it would be really interesting to pair humans and robots in the field, because right now it's very scary to be operating near a robot. We don't have a lot of guarantees for safe operation close to robots. So what I would love to do is map a cave and have my little robot partners help me so I don't have to go through those tight, terrible passages. And so I think having like a one robot human team or multiple robot human team exploring an environment would be really interesting.
That's very cool. Basti, you have a smirk over there.
Yeah, I mean, I think a lot of the challenges are driven, I guess, by requirements from outside, like not what we want. but I think, if I had to pick a fun one, I think it would be putting, aerial robots to work, like beyond ISR and cargo, right? So, painting, drilling, manipulation. I think that would be a really good, fun challenge.
Yeah. Kyle, over to you.
Yeah, I'd really like to see a JADC2 style challenge where you can incorporate some of the different domains together into something. It really requires you to span the gamut from strategic down to tactical.
Yeah, no, that sounds great, and also very hard, as you know.
Indeed.
That's great. We'll jump to the next question here, which is, what new advances in robotic propulsion do you find most interesting or promising or useful? So I think this is getting at maybe at the core of mobility, and both maybe from an energy perspective, but also a locomotion perspective. I'll start with Basti. What do you think?
Well, I mean, so from a flying robot side, I think there is a lack of propulsion. So, and I think we definitely need better batteries or hybrids. Power that's compact, I think, is something. Also, there are questions on the propulsion from a propeller and maybe variable pitch, constant speed on smaller platforms. So I think there's a lot that could be done there, and also just the design space of the system itself. Like, where do you put the props? How do you have them? And yeah.
So, Ali, how about you?
Yeah, I think I sort of maybe answered a slightly different question. From the locomotion perspective, I would say we are tracking soft robots. That's a really interesting area for me. I'm really tracking and see if somebody would be able to, make a soft robot walk or move, because I think if we do that, it would change a lot of operations and autonomy and things like that. That would be an interesting one. But from the traditional ones, I guess the one area locomotion that is growing really fast is legged and platforms with legs, four-legged or bipedal. I think we have seen dramatic advances in the last 5 years or so, and a lot of companies come in that area. So it would be very interesting to track that and see how far they can go.
Any other thoughts on either propulsion, mobility, locomotion, even energy and power?
There's some new types of aerial systems that have come out, the coaxial, that have been really interesting. So I'm excited for those.
Yeah, and I'll answer more towards the energy side. I'm really excited about some of the in-air recharging ability and the potential that you could have more of a lifespan to your aerial platforms. That will enable a lot of new capability, I believe.
Yeah, absolutely. I think we've seen the limits of limited batteries, how that changes how we think about solving the problem, either from a logistics point of view or from a mission execution perspective, and designing systems around those types of constraints would be great to unlock.
Precisely.
For sure, that makes sense. Next question is, what is the biggest hurdle in the evolution from an uncrewed platform, namely teleoperated, to a platform that exercises autonomy in its mission? So I think this question is asking, how do we cut the umbilical, so to speak? Where's the first place you would look to do that? Basti, I'll start with you.
Yeah, I mean, I think it kind of comes back to this envelope analogy, right? If you get into an airliner today, it can fly from takeoff to landing without any intervention. But if something goes wrong, you still need the pilot. And I think the question is, can you think of how do you solve that problem, right? Do you try to come up with all the potential things that go wrong, or do you have a system that can infer and do these things, right? And so.
Cool. Kyle, anything to add?
Yeah, I think you got towards a little bit of human-machine interfaces before, and having the ability to task via objectives, what you're trying to accomplish, rather than what you want the robot to do, I think is a big piece there. So hopefully we can advance that.
Yeah, absolutely. That brings us to the end of our panel discussion here, and I'm really excited, and please let us thank our panelists for sharing their thoughts this afternoon.